Hello, boys and girls. So I have to say I'm very happy that people in the blockchain space are generally pretty experimental in the sense that it's approached as an engineering field by most, but nevertheless you find a lot of solutions where it's not clear whether they are working in practice, and people propose white papers and so on and so forth. And so, for example, I was talking about linear logic as it pops up in the Libra Move white paper, and a little bit mentioning how it relates to linear types and type systems. And of course, my channel is kind of always trying to get the logical linear logical and type theoretical aspects into it, and I try to merge it with foundations. Eventually I want to get back to more statistical physics, but it all ties together in the sense that all these tools give you the capability to form models. And the nice thing is that even this experimental engineering space ties so much into these fundamental structures. And so there's linear logic being played around with then in project like R-Chain, which is also a Scala project. Scala being Java virtual machine language with a more elaborate type systems with subtyping and so on. And the R-Chain project is they are almost too academic to to get off their feet, because they are very unapologetic in the way that they write their blog posts and so on. They are like on this level, I would almost say. And then recently I read a paper by the Phantom project, and if you look into that on page 11, you have modal operators, which is an older notion from logics, non-standard logics. So you see that this quite I don't want to say non-mainstream because it's researched, but the stuff that you don't usually have to learn if you just want to cursory course on logic. These things pop up. And so what I want to do in this video, already 3 minutes in, but I come to the point here, for the sake of not having it to explain it on the side while doing a bigger video, I want to give people a kind of feeling for the pluralistic world of logics that are out there, right? So here we had talk about modal logics and linear logics, and even applied to discussions in white papers in an engineering field like the crypto space. And so I will make use of this in future videos, whether they have to do with blockchain or not. And what we always contrast against when we speak about quotes unquote non-standard logics is the propositional calculus or the predicate logic calculus, or the predicate logic. So, right, I was talking about this set theory book recently, right? And of course, these set theories, they are standing on established and well pathed out, I'm not sure if that's a word, logics, but there are also people trying to do set theory in other logics. And even if you are sitting in a framework that is as classic as propositional calculus, it helps tremendously if you understand other logics and other ways to phrase things. And what do I mean by logic here? A logic is, in a very abstract sense, if you want, a formal framework where you can express statements, and you always have some foundation, some axioms, and also in the foundation some rules of derivations, rules of inferences, and then you establish from a few sentences axioms, more sentences, and you assemble a basket of statements in that sense. And this is where I'm here coming from, is the syntactic approach, and that's also what relates more to type theory, right? Because the brutal thing about something like the propositional calculus, which describes a logic which is like a binary logic where you have truth value assigned to any statement. It's either true or false, yes or no, 1 or 0, and that breaks down a lot of possibilities. You can then go on and axiomize a fat theory using this logic. You can use the logic, introduce some fundamental objects. It don't have to be sets. You can do a lot of things in type theory if you add some rules, or you can do more abstract and do category theory to express these things. But eventually, nevertheless, you will end up with some notion of collections because it's useful for data structure assembly. And then you can use those big structures to express a lot of things. You can encode things, right? If you have data structures, you can encode things, and how do you say? There's this English expression, an indirection, right? You can have things represent other things, and that's why you can eventually use, for example, sets to express other things, and that's why it's stuck. And whatever, like some people don't want to or don't have to learn other things because they have assembled a huge data structure framework like a set theory to express other things in, and suddenly everything fits into the set theory. But if you go away from a binary logic approach, then you realize you can use syntactic expressions to talk about things much more directly, and even though they have a semantic realization or several, on the syntactic side you have a sharper, more direct access. And so what I want to do here is starting out with the propositional logic. I want to kind of raise awareness for notions you might want to express, which would be maybe cumbersome to express in the classical approach. So I will read you out a bunch of awkward, boring statements to make points. Okay, so this relates, by the way, to a video I did some weeks ago where I talk about logical connectives. I introduced them and I code them up also in Python. I did that to talk about SHA-2 because this is basically an algorithm that requires low computational complexity. It's a bunch of if branches, really, flipping around zeros and ones. So that is akin to the truth value semantics of classical logic. But the origin is, of course, here in the propositional calculus, and so I will also use these connectives. If you recall, or if you know, the classical connectives that are, you can define many Boolean valued, like two-valued functions, right? There are infinitely many if you have arbitrary many input arguments. But if you just consider the Boolean functions from one variable to another, then you have two. You say either the identity, you just return the value, or you negate it, you flip it, right? 0 turns to 1, 1 turns to 0. So that's on functions with one input argument and one output argument, where both are Booleans, right? We are now in this classical context where everything is Boolean. And then if you have more input argument, then you can make more functions. For example, you can consider the end function, which only returns true if both input arguments are true, or otherwise false, right? So I will make free use of these connectives in writing, like spelling out some basic sentences here. Okay, so I make some statements now, right? It is night, or it is night outside, which happens to be the case at this very moment where I record this at 10. That would be one statement, right? That would deal with here in a logic. Another would be it is day outside, or it's day, right? Another would be the negation of the first one. It's not the case that it's night outside. Or another statement would be if it's not the case that it's night outside, then it's day outside, right? Something which is binary statement, and can say here's a true statement. Then here's another statement. If it's not the case that it's night outside, then it's night outside. Right? This is not factually true. You can easily argue, right? If I say this is a book, so it's not a book, right? Or if it's not the case that I'm wearing a shirt, then I'm wearing a shirt. This is a statement, but it's like one that we judge to be false. I just want to make the case here that if I say statement, doesn't necessarily mean that it's a true statement. But in practice, we're mostly interested in what's true, and so mostly when we express statements, they're true. Okay. So another statement. At least one of those is true. Either it's night outside or it's day outside, or either it's night or it's day, right? Or either it's night or it's not night. It's not the case that it's both night and not night at the moment, or outside, or whatever. I can buy sugar. If it's the case that it's night outside, then I cannot buy sugar. If it's the case that it's night outside, then I cannot buy sugar and it's night outside, right? So if it's night, then because the stores are closed, I cannot buy sugar, and it's also night. Like this is like I repeat just the conditional proposition. Okay. I'm not at work all day. I'm at work all day. It's day outside and I'm at work all day. Or it's day outside and I'm at work. It's day outside implies that it's day outside or it's night outside. But it's also like classically surely true. If it's day outside, then it's day outside. And it's also the case that if it's day outside, then either of those is true. It's day outside or night outside. If it's night outside, then it's either night outside or I can buy sugar, right? So these statements are odd because, like, if it's night outside, then it's night outside and something else. That's surely true. I mean, if it's night outside and then it's night outside or whatever, like I say, in this case, I talk about buying sugar, whatever. I'm just assembling here basic statements and with this connected build bigger statements. Trust me, I will have a point here. Okay, so two more of these odd statements. If it's day outside, then it's day outside and it's day outside, right? I just repeat it, that it's day outside. If it's day outside and it's day outside, well, then it's day outside, right? Okay, here's a longer one. If it's day outside and from it being day outside, it follows that I can buy sugar, well, then I can buy sugar, right? So I have two things, it being day outside, and on the other hand, from it being day outside, it following that I can buy sugar. Taking those together, I can buy sugar. I mean, we judge this to be true. The last one, like proposition and implication leads to implication. That's one of the main rules of inference in the end that you use to operate on a classical logic level. We will get to that probably in another video, but I will now give you like again 4 more classical statements, and you will be able to in your head make a conclusion. And this is a case of a classical situation where you can, if you formalize propositional calculus, make a derivation. Okay, so the 4 statements, these are the 4 axioms for a framework now, are it's either night outside or it's day outside. First one. The second one is if it's night outside, then I cannot buy sugar. The third one would be if it's day outside, then I'm at work all day. And the 4th axiom is if I'm at work all day, then I cannot buy sugar. Okay, from these 4 axioms, you can conclude I cannot buy sugar, because either it's night and I cannot do it, or it's day and I have to work and I can also not do it. So here are 4 statements. One is disjunction from it's either the case that night or day. Like this gives me this doesn't tell me whether it's night or day, but it just tells me one of those is true. And then you have a bunch of entailments, a bunch of implications that taken together, if you chain the entailments together, lead to the fact that I cannot buy sugar, right? And if all the axioms are true, then I can conclude other things that are longer or shorter, right? I can conclude in this case. I mean, I didn't give you a formal derivation here because that's what formal logic is for. But this example is so basic that you can, immediately you don't need any computers to compute. Oh, that implies he doesn't have the option to buy sugar. Okay, so that being said, we can now express a bunch of truths. We have these fundamental building blocks, the propositions. In this case, the proposition would be it's night outside, it's day outside, I can buy sugar. And from which I build then it's not day or it's not night, or I cannot buy sugar. And disjunction and conjunction, so like and or implications and so on and so forth, and talking about work. And this is the framework in which you then can introduce maybe more connectives like inclusion, and then build a set theory in it. And then if you have set theory, you can have data types, and then you can construct a lot of things, and you can represent a lot of things as sets, and then you can basically express whatever you want by indirection, referring back to sets that represent things, or by introducing numbers built from sets and representing things. But the point here is the point for talking about logics in the plural and the pluralistic approach is that you can also go beyond just using the logical connectives and introduce and also quantifier as you use them in predicate logic. But you can be very creative. You can do reason about propositions as the variables, and you can modify and add modularity to propositions and do all kinds of things. Or you can actually take a classical logic framework and reduce logical axioms, rules of derivation maybe from it, or maybe I don't want to go ahead and talk about Hilbert systems, but just strip axioms away from your logic. One of the best known examples is passing from propositional logic to the weaker interactionistic logic, which closely ties to constructive type theory. But for example, here I will now make statements that don't directly fit into the binary logic world, meaning these statements can be expressed and be computed with in a way that you could say go beyond what the classical logic allows you to say. But of course, again, I have to emphasize that if you do modeling around it and do indirections, then you can reason about them, but not directly in this way, and you cannot do pen and paper work as easy because you have a big structure. And so if you want to do a more syntactic direct approach, then things you could talk about would be things as follows. So I make up a short story. Let's say you get kidnapped and get one over the head, and you fall asleep, and then you're locked into some room that has no windows, and you wake up and what happened? You don't even know how many days passed, and you have no sense of time anymore, right? So you're now in a situation where you don't know what actually the time is. So you could now say, well, it is the following statement holds. It's either day or night, right? It's assuming there's a sharp jumping over point between day and night. You could say there's day and night, but you can also now make statements about your perspective, your subjective reasoning, and you can say maybe it's day, right? And here you have the statement it's day, or maybe it's day outside. You have this statement it's day outside, and you add a modality to that. You say maybe, or you might say, well, maybe you have a watch and you believe your watch is 100% accurate, and you see, oh, it's that's a, you know, let's say the watch tells you PM and AM, and you see, oh, it's very, very late, and you can say, I know that it's night, right? You have the knowledge. Or you could say, I know that it's not night. Or you can say, it's not the case that I know that it's not night, which means maybe it's night. You can make other statements. You can say, maybe it's night, and I mean, here I'm also, still use the logical connectives. I can still say maybe it's night and maybe it's night, right? This is like, as you can still use the and. But I can, for example, say, it's not the case that maybe it's not either night or day. Meaning, it's necessary that it's now night or day, right? Despite me not knowing whether it's night, or me not being sure whether it's day, I can be sure about that it's either night or day, right? The modality, the uncertainty talks about the whole statement. And I can say then, I don't know, for example, it's not the case that maybe it's day, that as you can reason about, it's the same as saying it's necessary that it's not day, right? If it's not the case that maybe it's day, then necessarily it's not day. If maybe here means it's possible, right? So this would be the classical modal logic that you talk about possibilities. And again, you can do now set theory and find semantics, like structural descriptions with data types that spread out to possible futures, and then this possibility operator can be translated like you can translate propositional logics to zeros and ones. But on a syntactic level, you can describe this as is done, for example, in this phantom paper, right? This is a paper about BFT systems from Phantom Lab, and well, now I will not find it again. I think it was on page 11. Here, I mean, they don't use it extensively in this paper, but here you have use being made of this modal operators and K for knowledge in this case, I think. And so there's a kind of syntactic way of speaking about entailment. I will not try to give a crash course here on modal logic, but I want to point it out. And similarly, I want to discuss, take these examples that I used to speak about another situation which you might want to describe with a non-standard logic. Okay, so we talked about being able to buy sugar, right? And I can say, if I can buy sugar, then I can make cake. So there's an if then. This is some notion of entailment. I might want to express something else. I could say, if I have sugar, then I can have a cake, make a cake, have a cake. Maybe there's some time gap between, I cannot, if I say if I have sugar, then I have cake, might not capture the notions that I want to express, actually, because it's not the case that I have to take the sugar and have both at the same time. Having is this kind of present moment expression. And the funny thing is that, as I will quickly go through some Wikipedia pages on the end, that these kinds of notions you can express with modal operators as well. And so you might want to express that if I have sugar, then I can turn it to cake, right? In this turn, there is the timely notion baked into, and no pun intended. So if I have sugar, then I can turn it into a cake and have a cake. And so if you now compare, like before I had some statement like what would be a good... Yeah, I said if it's night outside, then I cannot buy sugar and it's night outside, right? So if it's night outside, which is the case, then because the stores are closed, I cannot buy sugar, but it's still night outside, right? And here you see that an verbal notion like entailment, like in logic, you might know it's like just the arrow to the side. If I mean this to say can turn into, like if I say if I have sugar I can turn it into cake, then this rule that is applied when constructing the sentence about night and buying sugar that I just said doesn't hold anymore, because the following does certainly not describe what I wanted to say. If I have sugar, then I can turn it into cake and I have sugar, right? If using the sugar uses up all of the sugar to make cake, then it's not the case that I have sugar, turn it into cake, and nevertheless still have sugar, right? So there's a difference. If I say it's night outside, implies that I cannot buy sugar and it's night outside. Being night outside is on both sides, and there's this arrow in between, which of course has two different meanings. But in the other case, having sugar, turning it into, like entailing and turning into having cake, and also having sugar is not true because there's something being used up. Of course, here different ideas are expressed with similarly structured sentences. And what you do then in non-classical logics is find similarities, but also break where, despite other similarities, some rules can't hold in both systems, and then you have another logic. That's what we have these sentences, and we use rules to reconstruct new sentences, and the meaning behind them might be different, but there are so many not just syntactic or but also like structural in the written down symbols. I guess that's kind of entailed by the syntactic similarities, commonalities that these make for different logics. Okay, so I hope that made sense, and you are now convinced that you might want to have different syntactic frameworks to express different circumstances, and the pluralistic perspective is kind of that you don't want to just model all the things in the classical approach. You can, of course, construct systems, but if you want to express them directly, then you go for these other logics. And so I already showed you that we have some modal operators in papers like this, and this is also not like new or surprising. I have a video already on this blue eyes puzzle where that was on a book on algebraic topology for distributed systems, and there is naturally to speak about common knowledge. What does somebody know? What does somebody believe? And what are the options for different people? And that's where these modalities, like these subjectivities, come in. And there is such a thing as subjective logic and probabilistic logic. And now I'm just going to show you some of the logics. So As you might have noticed, move, this is this type system, like this programming language by Facebook with the type system that has this resource management baked into it, and the inspiration, as you might have seen, is the same as the syntax underlying my cake example, right? Here you turn. What do you do here in this case? You moved currencies from one account to the next, like you do on Ethereum. But this type system, which is based on this, inspired by the linear logic, and there's a strong syntactic connection between the two, gives conditions to have this guaranteed for smart contracts running on the blockchain. Okay, so propositional logic. Well, here these substructural type systems, or substructural logics. I don't want to go on a million Wikipedia pages, but there's a lot of things on this, of course, right? So they use exactly once appeal that comes with the type system of move, has a corresponding so-called linear logic, this resource logic. And my example with the cake, that you cannot say I have sugar, I turn it into this, the entailment here in this logic, turn it into cake, and also I have the sugar and the cake. There's this connective, and how you implement this logic is by actually making weaker rules about disjunction and conjunction, so about and or. You create this logic, but by just stripping pieces off, if you will, classical logic, and also introducing some operators that are not present in the propositional logic. And so here we speak of weakening and contraction. I might make a technical video at one point about this, but so you have these both removed, and then you have this exactly once property in the type system. And here it says also speak about ordered type systems, which are even more restrictive, because if I say it's night or day, then you can also say it's day or night. Expresses the same thing, because this disjunction as well as conjunction is commutative. In an ordered logic, you don't even have this property. You're syntactically not allowed to switch them around and consider the new sentence thus produced to be valid. And here's some more, because I really like this Wikipedia page. This is one of the modal logics. So with these modality operators, you can necessarily talk about many things. One of them is believing, and here you have you can see them as kind of subjective logic modalities, and there are some properties expressed. I'm not sure to what extent you can read this, but I can translate it easily. So it says the switch around A means for all propositions holds. The B stands for belief. So okay, let's say B is what your mom believes, okay, for the sake of it. So for all propositions, it is the case that if your mom believes the proposition, then it's actually true, right? So if your mom is like very logical person, then if she comes to the conclusion something should be right, then it's actually right. This is what this statement says. And this is the characterization then of an accurate reasoner, right? Your mom is very accurate. Because if this property holds, if this is true, like in a Boolean sense, if you will, it's either true or false for your mom, let's say it's true, then for all statements, if she believes the statement, well, then you can actually know that like this thing guarantees, then this is actually the case. Like if your mom believes that eating too much sugar is bad for you, then it's actually the case that it's bad for you. An inaccurate reasoner would have a following property. There is a proposition such that the proposition is not true, nevertheless the inaccurate reasoner believes it. So for example, okay, your mom might believe that you can go 10 years without drinking water. just made it up in my mind. So let's for the sake of it say this is a wrong statement. So there exists this statement. The statement is false, but your mom might believe it. So if this characteristic holds for your mom, B being immediately intimately tied to your mom, then she would be an inaccurate reasoner. And so you also have this here, this K meaning I think in this case somebody knows something, K for knowing, and the I is the index of this person. So you might, it's been a while since I skimmed through the paper, but you might, for example, take a collection of people, like say everybody at your working place, give them all an indices, like you enumerate all these people, and then you have this person knows, or this person for this logic believes, and then you can play around and talk about what people believe, and maybe even about each other, and so on and so forth. Okay, let's just finish some more of those because I really like them. So let's do this. A consistent reasoner. So for the consistent reasoner holds these two properties. They are actually equivalent, I think, classically speaking. So for example, for the consistent reasoner holds that for all statements, it is true that if the consistent reasoner believes the statement, then it's not the case that this consistent reasoner believes that it's not true. So if the proposition, if the statement is believed by your mom, then it's not the case that your mom believes that it's not true, right? I mean, this is kind of classically, this is indeed very tautological, right? If your mom believes it, then it's not the case that she believes that it's not the case. I mean, if you remove the modality here, then this could be translated to if you know that if a proposition is true, then it's not the case that it's not true. Right? It's not the case that it's not true. And if you go in the other way around and make the statement that if it's not the case that something is not true, well, then it's true. Or if you do this double negation elimination, then you have also a statement of classical logic, which does not hold in logics like intuitionistic logic. But that's just a side note. So the okay, I didn't plan for that, but we're already at 40 minutes almost. So there is then modeling of temporal processes where you have some proposition, some sentence, in this case psi, and we can reason about it being true until a certain point, right? So maybe I'm on a diet and I'm consistently on a diet, and maybe I'm now overweight, but it will not always be the case that I'm overweight as long as I stay on the diet, right? There are statements which you can, if you don't fix them to the temporality now, change truth value in that sense. And so then here you have then these operators, like this is also modality. So we are still in the modal operators playground, so to speak. So we have for example G representing it will always be the case, and F representing it will be the case at one point in the future, that so F future, G like forever. And then you can say, well, if it will be at some point in the future be the case, then it's not the case that it will always be the case that it's not the case, right? So if somewhere in the future I will visit a friend in the US, then it's not the case that it will always be the case that I don't visit a friend in the future, right? Because it will happen at one point. And you have these double negation games, and if you were to go to quantifiers in the predicate logic, then you will see this come into play. So, and negation is dangerous. You see these kind of syntactic rules. You talk about different things, right? Believing certainties, future past reasoning, and nevertheless there's this syntactic equivalence or similarities, and then you have a bunch of modal logic as well. And so classically you have a very simple semantics, namely every proposition can be mapped to some truth value, boolean, true or false. Logics like modal logics also have semantics, but they're much more complicated. You might want a bigger setup, maybe coded up in set theory. And the modal operators also then, based on whatever the inputs are, have a simple binary function output. For example, if P and Q are two propositions, two statements, then if let's consider P and Q as a statement itself, then if P and Q are true, then P and Q is together is also true. If P is true but Q is false, then to claim that P and Q are true together would be wrong because one of those is false. So if one of them is false, then it's false, and so on and so forth. So this is the simple semantics. And here you have Boolean values. But then, for example, you have tree-valued logics where for AND you still have the old rules, right? So if A and B is both true, then this is true. So you read this in this way. This is the one statement. This is the other statement. This is the statement together, A and B, or what previously was P and Q. If both A and B are true, well then A and B together is also true. If one of them is false, like if A is false and B is true, then this is false. But then you also have unsure or uncertain, unknown. If and in this logic, in this particular logic, which is defined in this case via its truth value semantics, where there are three truth values, if A is uncertain and B is false, then A and B together is still false by this logic. If both are uncertain, then A and B is also uncertain, and so you can play around with that, right? So the negation of true is false, the negation of false is true, but the negation of uncertain is still uncertain. So you see here you have another logic. It extends actually just the propositional logic with more values. It is related, you might say, to modal logic, where I talked about I know, I don't know, this subjective approach. Although in this case, here you have particular values that are declared, and so the general semantics usually used for modal logics. I mean, I don't know to what extent you can bring them together, but the classical so-called crypte semantics are definitely harder than just this top-down definition by semantic truth values. And then you can extend this, right? You have many value logic, and then you have fuzzy logics, probabilistic logics. I will not mention them even here more than that. You have intuitionistic logics, which are the non-classical logic, which are almost getting mainstream, where you reject the double negation elimination, or where you reject the law of excluded middle, really. But before I said it's either it's either they or not they, right? So either of them is true, the one with affirmative sentence, or the negation of the sentence, affirming the negation, which ties also to the modality scenario where I said you wake up in the dark room and you don't know if it's day outside or night outside, where you also cannot say for you subjectively it's true or night, and you see how these things play together. And then some of these models are interpretable in others, and some are stronger and weaker and can be embedded, and so on and so forth. And then you can also embed statements of they're classical in that actually are not true in propositional logic, but you can embed them or come up with classically equivalent statements that can be the equivalent. I will not even go into that at the moment because it's getting too technical. But the intuitionistic logic that we just had is very useful given Curry-Howard correspondence that directly translates the logic to simple systems where you don't have double negation elimination. And I have a video on that. And there's then relevance logic, which is quite a bit different than the scenarios I talked about here. I could now go on and talk about the classical entailment, which I used initially to build sentence about night and day. And here, there's a logic popular among scholars in the southern hemisphere, so Australia and so on. This is also stripping away, in most cases, features of propositional logic, or there are also variants adding operators and so on and so forth. What I didn't even what I can't even touch here is things like paraconsistent logics, where you know, how did they say, in a non-discriminating way deals with contradictions. So you allow for contradictions in a certain sense. I mean, it's paraconsistent, it's not inconsistent. There's a difference to be made, and then there's also a lot to be said about judging the truth of statements, and then metalogical treatment of whether you have statements and whether you have inference rules and how they mirror each other. I'm not going to get into that at all here. And to close this up, I mean, I have some logics which I have some videos which go in the direction. So I have the blue eyes video. It's I talk about algebraic geometry probably more in this video, but it's really much about modalities, because it's about knowing. Then I have the video on the Kerr-Howard correspondence, and the video on logical connectives, which is easy but might be worth a watch as well. And yeah, I guess I'll leave it at that. It's night time, and I wanted to make this short. This is even longer than all the Libra videos, but so it goes. It's good I covered some of the things that I need to talk about, so that if you don't have any formal logic background, at least believe that there is more out there than the binary logic. They're easy to implement, undergrad computer science, yes, no, 0, 1 syntactic things. And I will not talk much about computational complexity theory or even about language theory. I'm not a computer scientist, but this is all relevant if you want to build nice foundations, eventually do some statistical physics, some quantum field theory, and all these kind of things that I will get to at one point. So thanks for watching. Subscribe to this video, click like, and tell me if you're hooked on any of these topics and you want to hear more about it. Take care.